Hello, everyone. Welcome to another tutorial by the Engineering Super Cloud Computing Division at the British University in Egypt. My name is Ahmed Torky. I'm a lecturer at the Civil Engineering Department, and I have again with me today Dr. Sherif. Hello, Dr. Sherif. Dr. Sherif
Hi.
Sorour.
Hi, everyone. Nice to meet you again.
Dr. Sherif is from the Mechanical Engineering Department, also at the British University in Egypt. So in today's tutorial, we're going to be talking about specifically coding, Python coding in Rescale. More importantly, the purpose will be for artificial intelligence algorithms. And I'll be covering a few ideas first here in this presentation. So the main purpose is to compute in Rescale, but I'll introduce quickly what kind of algorithms we'll be computing. If you're looking to follow us with like the available codes we have, I have it online. You can scan this page. It's on GitHub, and codes are available freely. So one of the things we're interested in engineering is finding optimizations of specifically design optimization of structures. We usually use evolutionary algorithms, of which are particle swarm and genetic algorithms. As you can see here, for particle swarm, you have several hundred particles dropped in a space. This 2D space is more like an oval, 3D oval. And right in the middle, in this spot, is the objective we're trying to reach. I believe here it's the minimal value we can get in the Z direction in this 2D space. So particles are dropped, and between iterations, particles come closer to each other as long as some particles are getting better fitness values than others, and pull the ones that are in unsatisfactory locations towards them. You can see it also here in 3D space. We'd like to implement this in Python with some simple problems. We can also try to implement genetic algorithms. We have here a population of 4 chromosomes. Each chromosome has 6 genes. You can imagine these as being each gene being, let's say, the thickness or the area of an element in a bigger structure of 6 elements. We're trying to find the optimal collection of, let's say, thickness or areas, sections, I mean, of elements. And as you might know, you initiate your population at first here of 4 chromosomes. You evaluate first, then you make a selection of them. You make modifications in them if it's not the first iteration. You evaluate, for example, here with structure analysis. If you're not satisfied with the optimum solution, you keep repeating this loop, and you discard any chromosomes that didn't perform well, and you favor chromosomes that performed really well and take them onto next generations, producing offspring from them. So here is one of the examples, very famous example. It's a 10-bar truss. You're trying to optimize the cross-sectional area of these 10 bars, and your objective is minimizing the weight of the structure, but however, you have constraints. You're trying to limit the deflection at 0.3 and at 0.5. By the way, they're all like pin connected, and you have 2 hinges here, and your loads are at joint 3 and 5, and you have some limitations on the maximum deflection. When you have smaller sections, it will deflect more. You can see here very briefly axial forces, compression and tension in each member. I've used both particle swarm and genetic algorithms here. You can see the videos. I hope it works. So let's say this limitation here is a violation. The particle swarms or genetic algorithms are a genetic algorithm is trying its best to find optimal mix of cross-section areas that doesn't exceed a specific constraint of deflection. You can see over here the real-time change in cross-sections. I believe these were I-beams. They can be C-beams, a C-section, or double I-section, as you wish. And we'd like to implement something like that in Python. And Chief, let me know if you have any questions. I can stop at any moment if you're curious about anything.
All right. Okay. I will.
All right. Thank you. And one other example I hope we were able to implement is coming up with a deep neural network that can predict a highly nonlinear function. For example, here, we're going to make a few compressive tests on concrete cubes. One of the very important tests in the construction industry, especially if you're using reinforced concrete, is to, whenever a batch plant supplies you with mixes, you try to test its compressive strength. So here there was previously a 1,000 sample test or experiment where we changed the input values for the concrete mix. And at the very end, we just have this compressive test that determines the capacity of each cube in megapascal. So we're going to use a deep neural network or dense neural network to try to map the input features, which are the concrete mix inputs against the compressive strength. So what are the inputs? Or what is the data set? By the way, you can find this data set by Cheng Ye. The paper is Modeling of Strength of High Performance Concrete Using Artificial Neural Networks back in 1998. You have here a sample of this huge data set of 1,000 samples, 10 samples here, I believe. You have cement, water, coarse aggregate, fine aggregate, age. Probably these are the inputs, and compressive strength would usually be the output or the target of the neural network. And we're going to try to implement this in today's tutorial as well. And I'm just going to go over these real quickly. No need to stress on them here. In a deep learning pipeline, you usually have this implementation. First, you get your data, features, and targets. Here, concrete mix inputs and targets are compressive strength. You'd have to clean your data and make sure you scale both inputs and outputs between 0 and 1. Dense neural networks favor that, both inputs and outputs. Split the data set into test and train or test, or train and validation and test, as you wish. Assign hyperparameters, which are the dense neural network relies on, like number of layers and number of neurons per layer. Train each iteration of hyperparameters. If you have a satisfactory model at the end, then that's it, you're done. If not, go change the hyperparameters and loop over this later part. So we're going to try to implement this now in the second part of the tutorial. So first part will be focusing on evolutionary algorithms. All right, we're here inside of the workstation. Going back quickly, the workstation I've chosen is it contains in the software settings NGC catalog interactive workflow, and it contains mini Conda interactive Ubuntu version. And as usual, I've chosen Grossler -1. It's the second generation AMD for the CPU, and we're using NVIDIA A10 GPU. Probably A100, H100 are favorable, but this is reasonably priced, so I recommend it. And we'll probably run our work at a reasonable rate. All right, so back to here. First of all, I believe we click here and write terminal. All right, we get this terminal over here. I think we can immediately check if there's a GPU here by clicking NVIDIA SMI. It didn't work. Okay. All right, so let's start with. Yeah. All right. So now we're back into. So now we've started with the workstation. We click over here and we open terminal. And first of all, let's on the side choose this command and run it. xdg-open desktop. So we have the desktop right in front of us. I have some files here in work shared. I'm going to be using these. Yeah, they're right here. Okay, and second of all, let's open Anaconda. So I believe Anaconda is already here, but we're going to create a new environment. So let's start off by clicking Conda help. So we have here the list of Conda commands we can be using right now. This is for anyone who would like to revise what flags and commands they'd like to use. I'm going to personally be making an environment as here. So Conda create, its name is AIEnv Python 3.9, and download the basic libraries you get with Anaconda.
Okay, so what are the libraries that we need?
Usually I have in each Python code the libraries I need at the start of the code itself. So for example here, usually whenever I write a code, I give myself an idea at the start. Oh, I'm actually going to use genetic algorithm. I'm going to use OpenCSpy. And I always help myself out with such ready commenting at the start of my Python code. So genetic algorithm, OpenCSpy, and over here, I believe we're going to need pip TensorFlow. So here I'll just say yes. So it's pretty fast on this workstation. Usually it takes much longer here in Egypt. All right, so here it's almost done. Probably 1 minute more and we'll be done with our new environment. We're going to activate it and enter the environment. All right, so it's ready. We're going to have this line to activate the environment, Conda activate AIEnv. So we have it here right inside of it now. By the way, we'll have to also install a few other things like Dr. Sherif just informed us. So we're going to have to install the genetic algorithm. We're going to have to install, but make sure you're inside of the environment when installing. OpenCSpy. This is a structure analysis software, and also TensorFlow, specifically GPU edition. I believe it already has a few things already installed beforehand. It should. So probably the next step is to open graphical user interface, which will for us be Spider. You can also choose to code in Jupyter. I prefer right now in Spider. So just click here, Spider. Spider has improved a lot recently. Honestly, favorite. So let's go to our codes right now. It's here in shared. So shall we start with the temporary truss?
Yeah, sounds good.
All right, so let's start with that one. This is a reinforcement learning problem. I usually implement such a thing in my training courses or with my year 3, year 4 students. Usually at the top here I have my units. I then have the upper bound of areas, the lower bound of the areas, the loading at each joint, the modulus of plasticity, the lengths of each member, and then you get this. You have to have a subroutine, which is the function of the 10-bar truss. So whenever a chromosome calls the 10-bar truss, it calls it with a collection of 10 um, 10 members, with each with randomly chosen cross sections for each between this upper and lower bound. And this is how OpenSeas usually looks like. Let me check up here. We've called it OpenSeas by OP. And no need to call OPS. I'm not sure why I have it here. It's all right. You can open a library twice. That's not a big deal. You have the truss elements here, 10 truss elements. Some parameters to solve your structure. And here, for each chromosome, you're going to have like a fitness calculation for it. Here, as you can see, we can get its volume and multiply it by its gamma for each member to get the total weight of the structure and add them subsequently or sequentially. And if deflection is violated by, I believe here, 5 centimeters or 50 millimeters in both x and y directions at each joint, you get this awful weight, which is like awfully big weight because you violated the constraint. And this lower part here, I just redo the run, but just for showing the output of the structure once it's ready. And at the very bottom here, I call the genetic algorithm. Here are the upper and lower bounds. We have 10 chromosomes, 50 iterations, or 50 generations. This is how you run the genetic algorithm. Sorry, these are the parameters for the genetic algorithms, like population size and mutation probability and so on. This is how you run your GA model. And at the very end here, it gives you the output. Why is this better on a workstation, even though it's not running on the GPU? These are quite hefty on a normal PC or a laptop. And maybe you'd love to run hundreds or thousands of mixes of chromosomes and iterations, make like a huge parametric study. It's better to have like an automated system and run it on Rescale rather than running it locally. And yeah, your computer won't be free for other jobs you might have. So let's run here 10 by 10, for example, or 10 by 20. Usually 10 by 20 would last, let's say, around 30 seconds, 20 seconds on my laptop. Let's see how fast it is here. Hopefully it would work. All right, it requires one more library. You can simply install it here, but you'll have to close the kernel and rerun again. So as you can see here, it's searching for an optimal solution. The problem here is that I'm outputting each iteration as cross sections. This could take a while. So let this run quickly. In my second run here, I'll run it again, but without this lower part. I can highlight it and click Control 1. And as you can see here, we're optimized to a certain extent after 10 generations. Let's see here. It should have been 20 generations. Population size. Oh, it's the other way around. Okay. All right, so here we have 10 iterations, 20 iterations, sorry, and population size of, because I think I should do this part again, so too many mistakes.
Okay, mungkin editing.
Right. And in the lower part here, we have calling the genetic algorithm library. We have 10 chromosomes, 20 generations. It's implemented here in the parameters. This is where the model part is. It calls the 10-bar trust the function at the top, and once it's done, it outputs the results here. At first, I'm going to highlight this visualization part and run it now. So as I was saying, it took maybe, let's say 15 to 20 seconds on my laptop. Here, it was pretty fast, probably even less than a second. You get the best cross-sectional areas here being output, and at the same time, you have here the fitness curve ready. One thing I didn't show here is that you'd have to install the Observis library, observation visualization library, the visualization library for OpenSeas. Once you've installed it, you can also visualize what each chromosome in each step is performing. It will take some time because it will output each combination that it's trying right now, which really isn't useful unless you're making a video so that your students, your colleagues in the seminar, for example, you can show them what's occurring in real time. All right, so I'm going to close this again, this visualization later part. I still have on the top here the calculation part in the 10-bar truss, and let's go crazy. So I believe that I remember, I mean to say like 50 and 100 here, it took a really long time. I would say it took maybe 15 minutes on my laptop, if I'm remembering correctly. Let's see how fast it's done here. Pretty fast, right? Let's try something even more crazy, 1000 generations. Although it's starting to settle here, it's not improving a lot. So maybe try more generations and more chromosomes. So how about 100 in 1,000? Let's see how fast this is.
Okay.
So it's still pretty fast. So it's doing 100,000 calculations. So it's going to finish it. Yeah.
That's a big number, yeah.
Yeah. So even without using a GPU, it's still more efficient here, running our work here.
Yeah, I can see that.
Yeah. And with 100 chromosomes, 1,000 iterations, you can see here, there was a plateau at 6,000, a weight of 6,000, but it actually managed to find better solutions and drop. Previously, we ran it at 100, I believe here. So it's still at 6,500. And if you don't have the processing power, you think that this is a plateau of non-improvement. So
okay, so it's a bit tricky in here, right?
Yes. One can easily be fooled by such plateaus because they really don't have the capacity to run more.
Okay.
Either resources or time on the computer, available time. So I'm actually pretty satisfied by how fast this is. This is a benchmark problem, so we can also check this with a publication, I believe it was in the 90s, for an optimum solution for this problem.
Okay, that's interesting.
Yeah, I honestly find this kind of work fun.
Yes, it is.
Yeah, it's maybe the nerd in me, and you're on board with me as well. But imagine having a more complex problem and finding economic or environmentally friendly solutions just by using such an algorithm on the Rescale platform. It's pretty good.
Yeah, that would be interesting, yes.
So let's go on to the next one. I'll try something quick before we go on to the concrete dense neural network. It's called the RNN sine cosine. So it's this one is pretty much fun. You have input in the form of cosine, and you want your output to be in the form of sine. So imagine you have a periodic wave. It's in the form of a cosine, and you want to predict a periodic wave that's in the form of a cosine. Like I've mentioned before, you have to arrange your input and output data. So let's have here a quick look from the start. This is where you call your CUDA device. I'm going to keep it at -1 running the CPU first. We're going to have 10 cycles, 5,000 time steps. Let's output this. Hopefully it will work. So this is what we have. The input data function in time steps between the amplitudes 1 and -1. Pretty simple, right? And you're trying to have the blue line and predict the orange line.
Okay, I see.
And over here, you have to make a few cleaning steps, organizing your variables so that you can pass it on to TensorFlow LSTM layers. We have here the start of the model. We use TensorFlow Keras. First layer has LSTM units of 16 neurons. Second layer is LSTM 16, and third one is LSTM 16 as well. Activation function is tanh. And the output layer is just one value at each time step using a dense layer. And over here, we're just mentioning the type of optimizer for this model. to optimize the loss mean squared error. And at the very end, we have here the fitting part, which is the training part. For just highlight here, 50 epochs. And then at the very end here, we plot the output. We make a few predictions, especially here, model.predict. And we have the actual output. We plot them against each other. Sorry, maybe there's trouble here, but okay, we can see it now. All right, let's run this code. So reset the kernel and run here. So LSTMs on a CPU, it's not the best of ideas. Each epoch takes 6 to 4 seconds. Usually the first epoch lasts longer because of the data transfer and initialization at the start, I believe. Yeah. There's a warning here, probably there's a change in the library itself. So 50 epochs would probably take a long time, even for such a simple task like this. Let's try to close this now and run it again. But this time, instead of running on the CPU, we run on the GPU. Since we have only one GPU here, we're going to change this to 0. Let me double check that we have the GPU ready. So here I'll click terminal. We need to start a new one. Activate our environment again. So we need to choose here. Let's try this again. All right, so we have over here, as you can see, CUDA version 12, pretty new. Let's see also what we can see here. The NVIDIA SMI driver, the version, driver version. What else can we spot here? The GPU version is 810G model, and currently a few applications are running on the GPU. We're using 116 megabytes or gig over here, and 1 gig in total probably. This is useful to double check again once you're running big applications to make sure the GPU is running. And 147, okay. All right, we're back. We had a very quick technical issue that will help you out. Make sure that your Python version is 3.9.19. We had to go back to double check one thing. So if you'd like to see over here, we've actually started the environment and recreated it again. We've recreated the environment with 3.9 and we've installed, I'll show it down here, pip install TensorFlow 2.10, just like this. Pip install TensorFlow 2.10. Make sure you install this one specifically. So you'll probably have to go back and recreate the environment from scratch, delete the old one, create a new one, Python 3.9, and then pip, once you're inside of the environment, pip install TensorFlow equal 2.10. All right, so we've done that right now. Maximize this. Let's start working here. So like we've mentioned before with Dr. Sherif, start off by running this initial part at the top. I've highlighted this part and clicked F9. As you can see here, our input data is the blue one, blue time series. It's a cosine wave, and the orange one is the sine wave. It's the output. It's the output time series. And if we revise here again, you have to have your input shape in this form, your output shape in this form. There's one time series as input, one time series as output. We've had LSTM layers. These LSTM layers are optimized to be trained on the GPU. Here we have NVIDIA A10 GPU. Let's close this kernel for now. For the very first layer, you need to define the input shape of your features. For subsequent layers, you have here LSTM with 16 units, another one with LSTM 16 units. All three of them activation function is 10H, and then finite dense layer. Again, you optimize with the optimizer Adam, optimizing mean squared error. We're going to run this for 100 epochs. Dr. Sherif, do you remember the older one? What was each epoch's time latency?
Yeah, if I recall, it was 4 seconds, right?
4 seconds, exactly. And here we're going to try something a little bigger. We hope it converges. And at the very end here, we'll make a model prediction. So let's see if we can beat 4 seconds. So we're going to run here. Make sure at the top here you have this as 0. It's ready here. It's going to start. All right, as you can see, we have 245 milliseconds per step per epoch. What do you think of this?
Okay, that's impressive, actually.
And even on personal laptops, it's much slower, even on a like laptop dedicated GPU. And as you can see here, the output quite perfect. The predicted values are in blue and they're in the background, and the actual values are in orange. If we try something shorter, go ahead if you have any questions.
It looks great actually. It's overlap perfectly, right?
Yeah. So 100 epochs for such a task just requires 100 epoch for such a task just requires 100 epochs. I've lowered it down to 50 epochs, and as you can see here, it's no longer that perfect as before. You have the perfect orange waves, they're the actual data, and the prediction from the model is its amplitude is weird, its phase is a little weird. And you can try here to increase the number of cycles. Let's take this 100 and this 50,000. Let's run this again with immediate inference, immediate predictions. Well, it's difficult to see. Let's see here. Let's lower it to 20. It might not work because my code is not ready for such a task, maybe. Predicting further type steps rather than quantifying. Oh, it's working. So some people might tell me like 5,000 steps, it's already accurate within the 5,000 steps for a recurrent neural network. What happens if you extend it even further beyond 5,000? Will it be able to keep the periodicity? So as you can see here, it's consistent. So it's working really well with time series, pretty fast. Let's go on to the problem we stated at the beginning of this video, the second problem. So here we have concrete data in a CSV file. You first have your input features, they're going to go to the X, and output are going to the data set. All right. You continue on to scaling your X and your Y data. Train test split 70% to 30%. Then over here you have your actual model, right? So if we zoom in a little bit, can you tell me right now what the first layer consists of? So over here it has a dense layer of 64 neurons, activation function ReDU. How about the second one?
Right, 16.
Yeah, 16.
The same activation function. Okay.
All the way down to here, the output being just compressive strength. So input features, you can get the shape of it from the dataset. All right, and
okay.
This part, you get the model summary, you can change epochs and patch sizes, you can compile your model, and you can start fitting it here. I equate it with this term so that I can plot the history curves later on. So if you look down here, you can use this to plot the loss and validation loss history curves, excuse me. All right, let's try running this. So here, I believe it will automatically go to the GPU, but because this is a dense neural network, sorry about that, it will probably already run quite fast. It's not as complicated as this one. Let's have this at the start here. Okay, so let's run this -1. Let's see how fast the epoch is. It's 4 milliseconds on the CPU. All right, I'm gonna let it continue. That's all right. So as you can see here, we have the training curve. This shouldn't be train, it should be train test or train validate. Where is it here? So let's run this again. So this blue line should be train, that purple line, magenta line should be test or validate. Let's see, yeah, quite consistent. It the best probably loss was here at around 40 epochs. Train continues as usual with overfitting. Here I have a few more plots. This just simply shows true compressive strength against predicted one from the model. Value should be lying on the diagonal. You can see here as well where the training dataset is. It's actually very dense, around, let's say, 10 to 50 megapascal. But here at the very end, like between 60 and 80, we have less samples, so it's expected to do worse at high megapascal. All right, so if it's 4 milliseconds on the CPU, let's see how fast it is on the GPU. Let's close this, run again. I expect it to be either the same or slower, because it's a very simple task. So it doesn't matter if you solve it on the GPU or CPU. We're going to check the output as well. And how can we really challenge it? What do you think we should do? This is the train test output. So, Sherif, what do you think we can really do here to make the neural network? Yes.
Increase the number of neurons.
Yeah, increase the number of neurons and layers. So increase this heavily. So it's a more realistic network. Okay. Let's go crazy all out like that. First of all, let's test with CPU. Let's hope it starts. Oh, 5 milliseconds. It's not really that difficult. Okay, so let's go for something even more crazy. 1,000. Okay, let's try that. 25. Okay, maybe we can give it another push. Let's go for 2,000. Okay, that's sufficient. All right, we're up to 50, 60 milliseconds. Now let's try that on the GPU. So there was a clear advantage with LSTM even for small neural networks. Here, that over there was recurrent neural networks, a little more difficult task to train. Here with dense neural networks, even with big neurons, we're getting 60 milliseconds. It's performing well. Let's see on the GPU. So the GPU wins finally. So when you have here huge and deep neural networks, the GPU clearly has an advantage. You have 60 milliseconds over there on the CPU and 10 milliseconds over here. And I really love how the code finishes up quite quickly, even with the graphs. You don't really get that on your personal PC desktops and on laptops as well.
Laptop or yeah, that's true.
So what I wanted to check was the model summary. Let's try to execute this point. And as you can see here, you have total or trainable parameters, 15 million parameters. But when you head here to the RNN CNN, you have here only 5,000 parameters. Yet the GPU is literally maybe giving you a speed up of, I would say, this is quarter of a second, and the CPU is 4 seconds, 8 times faster. Yeah. So yeah, this is what I wanted to show this time around. What do you think? Is it still worth it to the machine learning algorithms on a normal PC?
After seeing this, it's not worth it, I believe.
Yes, I agree too. And especially when you have a lot of input features and a lot of outputs, the trainable parameters become much more increased and much more complex.
Yeah,
So
I agree.
I would prefer to always run over here. All right, I'm going to close on this. Let's see what the last run gives us. So it didn't train that much. This task isn't a really complicated task. If you could check over here for my code. So for the first mixture, the prediction was around 50 megapascal. The actual was around 17.2 megapascal. For the second task, in the testing, I had a prediction of 34. The model was 39. Last one was 51 against 59. Doing reasonably well with some data cleaning, filtering, can do even better, I believe. And of course, this task, because it's not that crazy difficult, maybe these numbers aren't the best idea. Maybe we can have smaller numbers. So if we go back to this, for here, make sure that it's at GPU. And again, so let's see if it does any better with a smaller neural network. Not that much smaller, but yeah. You can see the validation was coming to a halt. Quite similar. Yeah, it doesn't seem like it's going to improve.
Okay.
All right, that's it for today.
That was informative and really good tutorial, and thank you for that.
I appreciate it.
Okay. Let's
Announce in the next one. We hope Dr. Samah will be with us, right?
yeah.
So if he agrees to it, we'll have MATLAB on Rescale tutorial next, hopefully. So that's it from us. It's improved slightly here and slightly here. That's it from us, Engineering Super Cloud Computing Division at the British University in Egypt, Faculty of Engineering. Until next time. Right.
Until next time. See you
See you.
the next tutorial. Bye bye.
Bye bye.